take a look at some applications of linear growth. So in these problems, I'm going to solve each of the problems, but first I'm going to write out a linear equation that can be used to solve the problem. We're going to jump right into some examples. So example 1, the average price of a 50-inch flat-screen television has decreased by $200 per year. If a 50-inch flat-screen TV cost $2,500 in 2015, what is the cost in 2023? First thing I'm going to do is develop that linear equation. I haven't been told what variables to use, so you could use x's and y's. It may also make sense to make something more, choose more meaningful variables. Maybe I want to use c for cost and t for TVs. I'm going to stick with x's and y's just to indicate those independent, dependent variables. So my y is going to be equal to, first thing I want to think about is the initial cost. The initial cost was $2,500. From there, the cost of the TV is decreasing. That number right there is my rate of change. That is my slope. So it's going down by $200 per year. So I'm going to attach my x to that equation. So here I'm letting y represent the cost of the TV, and my x is representing the years past 2015. This is all I was really asked for in terms of equation, but it's always a really good idea to think about what the variables mean. It might help to write out a little key like I've done here, or at the very least hold it in the back of your mind. Could I have also written it as y equals negative 200x plus 2,500? Sure, I could have, and that makes more sense in that y equals mx plus b format. I just a lot of times like to think about the b as a starting point, and then from there I'm adding, subtracting to it. Either way, we're going to get to this same equation. I want to know the cost in 2013. So we want to know the y, the cost, with the x associated be 2023, but that's not actually the x, because remember the x was the years after 2015. So if I want to know what year to use, well, the x is going to be 2023 minus 2015, and that would be 8 years. So the x we need to be using here is 8. So now I'm going to plug into my equation, y equals 2,500 minus 200 times 8. So I'm going to get my calculator, type it in exactly as I see it. And when we do this calculation, we get a total of 900. These would be dollars. So the cost of the television 50-inch flat screen will be $900. Let's take another example. Your cell phone plan costs $35 for the first 2 GB of data. It costs an additional $5 for each gigabyte of data that you use. How much will you have to pay if you use 5 GB of data? Just like before, I'm going to use x's and y's. So the y, the dependent, is the cost. We want to know the cost of this cell phone plan. It's dependent on how much data we use. So what is the initial cost? The initial cost is $35. From there, it's going to cost additional. If I'm over 2 GB, it's going to cost additional money. How much additional will it cost? $5 for every gigabyte I use. Now I'm not quite done. Let me define those variables just like I did before. So y is cost, x is the gigabyte, number of gigabytes of data, but past or after 2. So this equation works perfectly well. We just have to remember it's only true as long as we're past 2. If we used 1 or 1.5 or 0.2 gigabyte of data, then we would only be paying 35. This equation only works for x's greater than 2. Alternatively, we could also have an x minus 2 in here in the equation, but I think this equation will work pretty well for my purposes with the 5 GB. So what I need to do first, just like I did before, our x isn't just 5, it's going to be 5 minus 2, or 3. 3 GB of data past what my initial plan allowed for. So I'm going to plug in now 35 plus 5 times 3. 5 times 3 is 15 plus 35 gives me $50 for this cell phone plan. Let's move away from strictly costs. Let's look at another example here, example 3. Suppose a newborn baby weighs 7 pounds at birth and 10 pounds at 1 year of age. how much would you predict the baby to weigh after 2 years? What about 15 years? So the first thing I need to do is I need to get the equation. So y equals, starting weight appears to be 7, that's my initial amount. It's clearly going up, so I'm going to add. But here's the problem, I can't just put a 10x. It's not saying the baby increases 10 pounds every year. It's saying it weighs 10 pounds at 1 year of age. So I actually don't have the slope number given to me. I'm going to have to calculate that the same way we did earlier. So off to the side here, let's calculate slope. Remember, slope is y2, 10, minus y1, that was 7, the final weight minus the initial weight. The time that's passed is 1, or 1 year minus 0 years. Either way, you can just have 1 down there. 1 minus 0, just 1. So we get a slope of 3. This baby has increased 3 pounds in the first year that it was alive. So I'll have 3 times x here. 7 is the initial, plus 3 pounds for every additional year. Our y is weight, and our x, those are years. First question, how much does the baby weigh after 2 years? So after 2 years, that means I'm plugging in 2 for my x. We'll have y is equal to 7 plus 3 times 2. That would be 6 additional pounds, taking me to a total of 13 pounds. Let me go ahead and type this out. I'm going to create a little more space here. So the baby will weigh 13 pounds after 2 years. I was asked a second part to this question, which was how much will the baby weigh after 15 years? So after 15, I'm going to plug in that 15, so y equals 7 plus 3 times 15. And when we type that in, we get a total of 52 pounds. So after 15 years, the baby, no longer a baby, will weigh 52 pounds. Now the first calculation we did may seem a little bit small, should seem a little bit small. I don't know if you know a lot of 2-year-olds, but probably seems a little bit under. I think we know at 15 years of age, children don't usually weigh 52 pounds, usually considerably more by that point. So what happened here? We didn't do anything wrong. We used the equation correctly, the equation we built correctly, but we maybe shouldn't have used a linear equation here, or at the very least, that linear equation won't be true for extended periods of time. And so, again, for this calculation, we haven't done anything wrong in the calculation, but this is something we're going to be moving towards is, okay, which model is really the most appropriate to use? Here we're just assuming linear growth, and so nothing's wrong, but children don't grow linearly for their entire lives. Obviously, that's not true. People don't continue to grow forever. And so this model is only going to be valid for a certain amount of time, maybe from 0 to 2 years, maybe a little bit less, maybe from 0 to a year and a half. We don't know exactly without studying the model a little bit more, but we want to be careful that whenever we build a model, that is not always true for entirety. Even up here in the earlier examples, that TV is not eventually going to become $0. If we keep subtracting 200s in 4 more years' time, that would say the TV is worth $0. They're not going to give you the TV for free. Something might change. Maybe they change the TV to be a better quality. Maybe the price goes up in other ways, right? Or here, the cell phone plans. A lot of cell phone plans now don't even charge you for extra data because things change. And so we want to be very, very careful. When we're building our models, chances are it's only valid over certain periods of time or certain scenarios. So that is one thing we want to be aware of moving forward. Let's take one last example. The city has a population of 75,000 people in 2010. It sees a decrease in population by 3,500 people each year. In what year will the population reach 29,500 people? So I'm going to start by setting up that equation. Y is equal to, we're looking at population, so the initial population was 75,000. It's decreasing, so we're going to have a minus 3,500 people per year. So every year I'm going to attach that X on it. Here, the y is the population, and the x, these are years past 2010. We have this 29,500. We want to be careful we're not just always plugging in for x. One of the reasons I'm doing this is I'm really thinking about what do the variables mean. We want to know in what year. We are looking for the x. The population is 29,500. So at 29,500, that's going to be the y here. We're going to plug that in for the y's side. We're going to have to solve this equation for x. It's not just simply plugging in this time. I'm going to have to do a little bit of math here. So the first thing I'm going to do is I'm going to subtract that 75,000 to the other side to get it away from the x. When I subtract, we get negative 45,500. That is equal to the negative 3,500x. My next step, I'm going to have to divide by that negative 3,500. When I divide by negative 3,500, I get a total of 13. Now my answer is not just 13, because we want to know in what year. So remember, x was the number of years past 2010. So to figure out the year, I need to add this to 2010, and that of course will give me 2026. So now we can answer the question. In the year 2026, the population of the city will reach 29,500 people. So we want to really be careful of and paying attention to what are our x and y variables. You may have chosen to use different variable names. I think that makes sense in a lot of cases. Maybe instead of x and y, maybe I use p for population and t for time, something like that. But still a good idea, I think, to go ahead and define what those variables are so you remember. When you're doing these calculations, you can remember what is it I need to plug in for, what is it am I looking for. I'm looking for the y, plugging in for the x, or vice versa. And once we get our answer, okay, is that the answer, or do I need to do something to that number? So it's very, very valuable to define those variables.